Hey there, my name is Gokul, and today I'm going to talk about our work on imitation learning in the presence of temporally correlated noise. Let me set the stage for why I find the problem of causal confounding and imitation learning interesting. So, broadly speaking, there's three classes of imitation learning algorithms. There's offline approaches like behavior cloning that learn purely from recorded demonstrations, online approaches like Gale that compare simulated learner rollouts to expert trajectories, and interactive approaches like Dagger that query the expert for action labels on learner rollouts. In an ICML paper last year, we proved performance bounds that hold for all algorithms in each of these classes via a bit of game theory. You could think of the epsilon term here as a measure of the training error. Now, if we take epsilon to zero, all three of these bounds seem to indicate that we should perform as well as the expert does if we have no training error. Unfortunately, in the real world, this often isn't the case. For example, in the autonomous driving domain, direct application of imitation learning methods with rich model classes and large amounts of training data can sometimes lead to policies that make systematically suboptimal decisions. This indicates to us that we're likely missing a key feature of the imitation learning problem that makes it hard in practice. Our goal with this work was to take a step towards handling a potential cause of poor performance, temporally correlated noise, or TCN for short. Let's dig into an example mirroring what the past work observed in practice that gets at the heart of the downstream effects of temporally correlated noise. Consider the problem of trying to learn to fly a quadcopter by imitating an expert pilot. Let's assume there's heavy gusts of wind that cause the quadcopter to deviate from the intended straight path of the expert. The direction of these gusts of winds will be naturally correlated over time. Now, what will happen if we try to apply a standard offline imitation learning algorithm like behavior cloning to this set of demonstrations? Well, the learner is likely to pick up on the correlation that being a little on the left is usually followed by going even more on the left. If they ignore the fact that it was the wind that was the root cause of these correlations, they might attempt to reproduce the swerving behavior of the expert, causing them to deviate even further at test time due to the continued influence of the wind. More abstractly, the effect of TCN, like the wind in our previous example, is to introduce temporal correlations in the recorded actions that do not have their true cause in the recorded state. We can visualize this effect via a structural causal model. At each time step, the expert takes an action responding to the observed state, and the MDP transitions to the next state. The persistent confounder U affects multiple actions. If we try to learn a policy via behavior cloning, that is by regressing from states to actions, we can produce inconsistent estimates of the expert's policy. This is because the TCN travels through the dynamics to influence the state at time t, as well as perturbing the action at time t, leading to spurious correlations between recorded states and actions. The learner might latch onto these spurious correlations and explain away the effect of the TCN by misattributing it to some element of the state, leading to poor test time performance. This is what leads to the increased swerving in our quadcopter example, with the wind's effect being attributed to the lateral position. What I'm going to talk about today are methods that can learn to fly as straight as the expert did in the demonstrations. More generally, the methods I'm talking about today are meant to handle temporally correlated noise in sequential prediction tasks. Our paper has a list of other examples of this setup. Now, how we go about handling TCN. One idea that might seem natural is to roll in the learner's policy in the environment and ask the expert to annotate states with what their preferred action would have been. So we would ask the expert for a direction they had intended to fly and train on these new action labels repeatedly. As these action labels are generated via direct queries rather than rollouts, they wouldn't be corrupted by TCN and would enable the learner to consistently estimate the expert's policy. In the language of causal inference, these sorts of interactive imitation learning algorithms are measuring the expert's response to the intervention of being placed in a certain state, and are therefore able to eliminate spurious correlations. Unfortunately, just like how randomized controlled trials are not always feasible, a queryable expert might not always be available. The methods I'll be talking about today instead focus on how we can learn from observational data, that is, collected expert demonstrations. Our approaches are based on a technique from econometrics called instrumental variable regression. Let's go through the key idea of IVR in a simplified setup. Consider trying to regress from x to y, both of which are influenced by a confounder u. Ideally, to mitigate the effect of the confounder, we would randomize over x via a controlled experiment. If we only have access to observational data, we can achieve the same effect via a source of randomness independent of the confounder. This variable is called an instrument, which we denote as z. The key idea of instrumental variable regression is that we can condition on z to cancel out the effect of the confounder. Let me make that statement a bit more formal. Let's write x as an arbitrary function of z and u, and y as a function of x with a zero mean u being added in. Our goal is to learn h. One needs an additive noise assumption or something analogous to use instrumental variable techniques. We reference an excellent article by Pearl that explains this point in greater detail. Under these assumptions, one can derive a set of conditional moment restrictions. U is independent of z, so conditioning on it does not change the mean. Rearranging our expression for y, we get a constraint that must hold uniformly over z. We can then attempt to satisfy these conditions approximately by minimizing the squared difference between the two sides of this expression averaged over z. To evaluate this objective, one needs to be able to draw samples of x conditioned on a particular value of z. One therefore needs to learn a generative model of p of x given z first, and then minimize the MSE over samples generated from this model. We show in our paper how this is equivalent to a particular zero-sum game that does not require a two-stage procedure. Putting it all together, we can derive two objectives based on a necessary condition for the causally correct predictor. For it to be a sufficient condition, one needs the natural identifiability properties to hold. We refer interested readers to the landmark work of Chen and Pozo for greater detail. Okay, so given an instrument, we now know how to filter out an unobserved confounder. Connecting back to the imitation learning setup, the past state acts as this instrument, as it is independent of future confounder. Graphically, this corresponds to the fact that s sub t minus 1 is independent from u sub t. While for traditional IVR approaches, determining a valid instrument can be quite tricky, the error of time enables us to use history as an instrument without concern. We can leverage the past state instrument in two ways, each of which corresponds to one of the instrumental variable techniques we discussed previously. The first is based on the generative modeling family of techniques. We learn a model of the inputs conditioned on the instrument, which in our context corresponds to learning a state transition model. One can draw fresh states from this model and then regress to the expert actions. Intuitively, because these fresh samples and the observed expert actions no longer share a noise term, standard regression will be consistent. In contrast, behavioral cloning, which regresses from states in a demonstration to their corresponding actions, will pick up in the temporally correlated noise. For tasks with high-dimensional state spaces, like images, it might be infeasible to learn such a state transition model. However, if one has access to an accurate simulator, one can instead simply learn a policy via behavior cloning and plug these actions into the simulator to get fresh state draws. While this first stage policy is biased, as long as its bias is independent from that of the demonstrated actions, we are in the clear. So, in short, one runs behavior cloning, uses the learned policy to redraw states, and performs behavior cloning again. These two applications of behavior cloning lead us to turn this algorithm double. We prove the bound on the performance gap with respect to the expert displayed on the screen, where C corresponds to the smoothness of the noise distribution, epsilon and delta correspond to errors in the first and second stage policies, kappa of pi, a problem-dependent constant that quantifies the weakness of the instrument, and t the horizon of the problem. Note that if both training errors are driven to zero, this bound implies we will find a value equivalent policy to the expert. Behavior cloning does not enjoy a similar bound in the temporally correlated noise setting because of the inconsistency issues just discussed. We can also apply the game theoretic approach and try to minimize the residual between expert and learner actions while letting an adversary that has access to the past state instrument weight the data points differently. As we discussed previously, this is equivalent to the generative modeling approach, but does not require a two-stage procedure. Note that this approach is completely offline with no need for a simulator. Practically, we solve this game via the optimistic mirror descent approach, which gives us fast and last iterate convergence. We get a similar bound that only depends on a single training error. Similarly, if this bound is driven to 0, we will achieve value equivalent to the expert policy. Putting it all together, we derive two different instrumental variable imitation learning techniques that have provable performance guarantees under temporally correlated noise. Both can be seen as instances of the base IVR techniques we discussed that use the past state as an instrument. In short, standard offline imitation learning approaches aren't able to handle TCN. However, IVR-based techniques are able to use the past state as an instrument to eliminate the TCN. Interactive approaches, which are able to perform state interventions via learner rollouts, are inherently unaffected by TCN. A natural question at this point might be whether standard online imitation learning approaches like Gale or maximum entropy inverse reinforcement learning are robust against TCN. If, as we assume, the simulator does not generate TCN, even rolling out the expert policy will lead to trajectories that are rather different from demonstrations. This makes it unlikely that comparing learner and expert trajectories will lead to a sensible training objective, making these sorts of approaches inconsistent. While we don't discuss it in our paper, an interesting direction for future work would be to derive a hybrid online IVR technique that is not affected by TCN, nor the quadratic compounding of errors that affects all offline approaches and can be seen in our previously derived bounds. We now turn our attention to the practical implementation of these approaches. Empirically, we find that both of our methods produce policies that are much more closely able to match expert actions than those produced by behavior cloning, as measured by mean squared error on environments from the pi-billet sweep. The policies we learn are able to match expert performance under the same noise distribution, agreeing with what our theory predicts. We next consider the generalization performance of our learned policies. After training them on samples from an environment with TCN, we tested their efficacy at predicting expert actions and performance on noiseless environments. We observed that the policies produced by our methods generalize much better than those produced by behavior cloning along both of these metrics. While it's hard to say much in theory about the effects of this sort of shift, we believe these experiments provide some evidence that we're recovering a policy that performs as the expert would under different noise distributions. One can also use our methods as a diagnostic tool to help identify areas where the effect of TCN is particularly strong. On the Ludo-Lander task, we plot the difference between the actions predicted by BC policies and causal imitation learning policies at various points of the state space. The red dots to the center highlight an area where TCN is particularly effective at corrupting BC actions. We also consider an extension to our previous graphical model, where a confounder can affect more than 2 time steps. For example, the wind in a quadcopter example might affect quite a few time steps before dissipating. This sort of persistent confounder means that one needs to reach back further in time to find a valid instrument that is not affected by the TCN. States further back end up being weaker instruments, as they are less correlated with the present. We plot the weakness of the instrument, kappa, for a linear quadratic Gaussian problem, and we see it grow exponentially with the persistence of the confounder. This tells us that the effect of a confounder that sticks around for a few time steps can be significantly harder to remove. Kappa is a feature of the problem rather than a particular algorithm. It in some sense captures how ill-posed the question we are asking is. So we would expect similar methods to have a similar dependence on kappa. With that, I'd like to thank you for your time, and please check out our full paper, code, and videos at the link on the screen. Feel free to send me an email as well if you have any further questions. Thank you again. Bye.